for the kind introduction and for the invitation to be here. This is the first time I give a talk at MSU, and I'm actually at MSU. I was here at a conference before. Can you hear me? Okay.
The microphone's not for the room, it's for the recording.
Oh, okay. Okay. So as Chris said, I am kind of a Gammaray astronomer. I'm a nuclear physicist by training, and oops.
Maybe move it up a little bit.
Hmm?
Maybe move it up a little bit.
The mic?
It doesn't come through the room.
So for the room, I have to speak up. Okay. Well, I am really happy to be here because I was involved in JINA from early on, and I'm a nuclear physicist by training. Then I got into experimental astrophysics by building Gammaray telescopes. Oh, do I need to stand at a certain location? Okay, thank you. And today I want to tell you a little bit about my field, which is building Gammaray telescopes, then making measurements with those and trying to learn from them. And so my talk will be structured in that way, that I first want to talk about the experimental technique and how that is similar and also different to what you are using or what you're doing when you are making Gammaray measurements in the lab. And then I will talk about two applications. One is supernova explosions, and the other one is transport of nucleosynthesis ejecta in the interstellar medium from one generation of stars to the next. So, starting out, I want to present you with the current facilities that we have to measure Gammaray lines from nuclei in the cosmos. This is Integral. Integral has been launched in 2002, so it's already aged in a sense, but it's working. It will be operating until 2029, and it was originally designed only for 3 years, but it works so well, and we make nice results, and so we are able to convince the agencies year after year to continue. I hope that will go on until we will have our orbit re-entry into the Earth atmosphere in 2029. So it's just a question of money. And just to give you a scale, the operations of such a satellite cost about 3 million per year. And that's paying the antenna and paying the experts that do the flight management. So in case you have an anomaly with the satellite, you have to have some engineers, some flight engineers. And this is the main cost driver for continuing. The whole satellite was not as expensive. It was about 1 billion. So at that time, it was much cheaper. But when you want to build a next generation satellite like this, you're talking about maybe closer to 2 billion an investment. And that has to be supported by the community. A smaller mission is NuSTAR. NuSTAR was launched from an airplane with a rocket. And this is an X-ray satellite, which also is figuring under nuclear Gammaray telescopes, even though it works only up to 80 keV. So it does not really do the nuclear line range, with one exception. And that one exception is the reason for this name. And I'll be talking about results from this. And I will be mainly concentrating on the lines that I list here. I have here a short version of the line list that only addresses the explosions that I want to talk about. I should add to this list beryllium-7 and sodium-22, which we have been talking about this morning with some people, and it's relevant for some people here. But the list of lines is fairly short, with only 7 or so isotopes, and it's limited by the constraint that the site of nucleosynthesis has to become transparent to gamma rays first. And so usually those sites are like supernova explosions. They are optically thick for the first few days. And that's why all the short-lived isotopes that you are dealing with here, they are irrelevant for us because they don't come out of the source in a cosmic source. So the shortest lived source isotope that we would be able to see is beryllium-7. It hasn't been detected, but it is suspected to be detectable from a nova explosion nearby. And then the shorter-lived chain starts here with nickel-56 with a decay time of 8 days or 9 days, the initial decay. Then the later decay to iron-60 is 111 days. And I'll be talking about this and an application in type 1a explosions. I'll also talk about a little bit about titanium-44, which is from core collapse supernovae with almost 100 years lifetime. And then there is this long-lived set of aluminum-26 and iron-60 with million-year lifetime. This is a time scale that is much longer than the time you can see a supernova remnant. So with those radioisotopes, we can actually trace what happens when you have nucleosynthesis out to millions of years afterwards when the ejecta have been spread out already in the interstellar medium. And I'll discuss that at the end. And I also list positrons here, which live in the interstellar medium for roughly 10 to the 5 years. We don't know that, depends on the environment. But this is also listed here because it falls in the same energy range of MEV type gamma rays. These are the energies that we need to target. And you see here, those are the two energies that are relevant for new star. The rest of the list is beyond their energy range. But anyway, they have contributed a very important measurement that I will discuss. Now, all of this has to be done from space. And this is the reason, because when you want to do astronomy, cosmic photons only penetrate the Earth atmosphere as shown here. So this is all atomic physics. So you do not see anything in the ultraviolet from the ground. Luckily, because otherwise we would get sunburn and it would be a little difficult. But this is all atomic physics in the Earth atmosphere. This is molecules in the long wavelength range. So some infrared astronomy can be done from high-flying aircraft, which is like the Kuiper Airborne Observatory or SOFIA. They have been missions here. And you can do a little bit of ground-based in the radio range, you know, the radio telescopes, and in the high energy gamma range. The rest is space physics. This is all part of what we call today multi-messenger astronomy. So I like to show the electromagnetic spectrum, and I then added the material probes here, which is the cosmic rays, neutrinos, and then we have astroseismology, gravitational waves, and pre-solar dust. I call them all messengers, and you can do astronomy with each of those. But the physics is very different. And what I will be talking about is this range here. This is the range of nuclear emission. And this is not common in astronomy. Most astronomy deals with atomic transitions of electrons in orbits. You have recombination radiation, and this happens for molecules and for atoms. So there's a lot of discussion about infrared and radio lines where you detect all the complicated, the complex molecules that can be found in interstellar space, including alcohol and complex molecules. And then the atomic field is pretty broad, and that's why most astronomers don't know the field of nuclear astronomy, and it hasn't been established, but we try to establish it with what I'm talking about here. So here are examples of all this multi-messenger. So this is solar neutrinos, this is high energy neutrinos, this is pre-solar grains, this is ocean crust. All of these are astronomies in my terminology, but not astronomies by terms of a conventional telescope builder. Now, gamma ray telescopes are not looking like normal telescopes, and they are more familiar to the equipment that you use in nuclear labs. Essentially, you have a detector that detects gamma ray photons, and you can turn that into a telescope by having a kind of anti-coincidence that defines an aperture. That's the most primitive way. You wouldn't call that a telescope normally, but it has been actually a telescope on the Gammaray Observatory that was launched in 1991. Then we had a refined version, which I will talk about with integral. This is the coded mask technology. It's basically as simple as this, except that you have a pixelized detector plane and you have an aperture that has openings and closures. So it's called a coded mask, and that coded mask casts a shadow onto your pixelized detector, and that way you can have like a pinhole camera, but you can have some resolution on the sky. And the real thing to be built and used is a Compton telescope, because gamma rays are so penetrating. So usually in the first photon interaction, you create secondaries that have substantial energy. They will not be absorbed locally. And so you need to have something like a tracking chamber. You need to be able to measure the secondaries in something like a time projection chamber that we discussed this morning, or a normal Compton telescope that consists of at least 2 layers of detectors. This is the future, and we had already CompTel on the NASA Compton Observatory some 15 years ago. So these are the principles. The difficulty of building optics for gamma rays is illustrated here when the wavelength of your radiation becomes as short as the separation between the atoms in any structure that you can build. Then you can think of the photons basically falling into the gaps, into the cracks, and you cannot build reflective mirrors anymore. There is a trick at X-ray energies, that is the grazing incidence, and then you can have different layers of atoms that have different spacings, and that's the multilayer optics that is actually used in X-ray telescopes. This is an example of an X-ray telescope, and I just want to use it as a reminder. The NuSTAR telescope has such optics there and detectors down here extended on a boom, so that you have the suitable optics. This is an illustration of the multilayer surface that the mirrors have, and this is the sensitivity curve that drops sharply at 80 keV. So you see that's NuSTAR. A Compton telescope makes use of the Compton scatter interactions. So here an incoming photon is deflected by a single Compton scatter in the upper layer of detectors, and then the scattered photon is absorbed in the second layer of detectors. So in CompTel, we used here a liquid scintillator and a sodium iodide. And so with this kind of interaction, you can constrain the incoming direction only to a cone that has the opening angle of the Compton scatter angle. And so you see that in this case, you have not focusing optics. You need to kind of invert that. So your computer on ground is actually part of your instrument, because you can do the imaging only in the computer. Each Compton interaction can have a different scatter angle. And so when you plot this potential arrivals direction on the sky, you get one of those circles. From the next interaction, you get another circle that can have a different diameter. And so in the ideal case, all those circles, they intersect in the direction where the source is located. But that already tells you that you get also a lot of noise in the rest of the sky. So imaging in gamma rays is difficult. It's limited by the fact that the Compton scattering here occurs on electrons, and those electrons usually are bound by an atom. And so there are different orbits that the electron can be on. And so the limitation, the fundamental limitation here is that you get a positional resolution that is on the order of a degree or so. And it's difficult to get any better than a degree in the gamma ray range. We have to live with that. The other concept that I will discuss is the coded mask. It's illustrated here. This is the SPE instrument on integral. It's based on germanium detectors. One of those is shown here, and we have 19 of those in a camera. These 19 detectors, they are illuminated through what's called a coded mask, and this is made of tungsten. And you see it has a rather complex pattern. That pattern has been a result of the mathematics of inverting different directions on the sky and making the patterns as unique as possible for different directions. That is a mathematical result of this. Now this sits about 1.70 meters above the detectors, and so here is the illustration of how it works. When you have a source in one direction, then you see that for this blue source, only the blue detectors will actually receive a signal, while the other ones are blocked from the radiation. When you change the orientation, you have other detectors exposed. And so we detect such shadowgrams. We want to find the pattern of detectors that respond to certain directions on the sky. And with this response, we can actually detect this above the background and can try and find out where the source are. This looks pretty simple here. In reality, we have these 19 detectors, and this is for the typical pointing pattern, the partial or full exposure of each of our 19 detectors for different directions when we do 2-degree steps around a source of interest. So we have this encoding in our germanium detectors that we need to find out. And I showed you the germanium detectors already, and I think you are probably familiar with those. We have the ones with the central anode, and they are encapsulated in beryllium. So this is one illustration. And the germanium detector spectra, they look like this. And probably many of those of you are working with that. Now this is a spectrum which is from, I think, from 1 year of our mission or so. And it's a log-log spectrum. You see that you have a continuum that falls towards high energies with a little bump here in the nuclear energy range. But you see, it's a continuum, and there are lines on top of it which have different shapes. So there are blends of lines, there are broadened lines, and there are narrow lines. We have 400 of those lines, and they are all instrumental. So everything you see here is not from the cosmos, from cosmic nuclei. It's from nuclei that are produced by cosmic rays in our spacecraft. Oops. Okay. Now this is the background that we have to understand before we can do anything with cosmic sources. And so we looked at the background and we looked at it over time, over the 13 years or 15 years that we have now in operation. And you see that this is the count rate per detector over 13 years. You see here that it rises to a peak and goes down, and then there is some microstructure on top of it. And this nicely anti-correlates with what is shown in the gray shaded histograms here, which is the solar activity. So what we are seeing here is basically the background is created by cosmic rays, and those cosmic rays, they penetrate deeper into the Earth atmosphere or less deep, depending on how active the sun is. It's a reflection of the structure of the magnetosphere. So this is the first order shape that you see. And now when you look at different structures, like for example, one instrumental line that comes from bismuth in this case, then you see that you see the same structure again, but there is a different microstructure. And this is for a germanium line. So characteristic isotopes have overall a similar shape, but in detail the structure is different. Now we can normalize this to the continuum to find a clearer structure. And so, for example, here you see buildup of cobalt-60 in our spacecraft. So just the fact that we are operating in space makes cobalt-60 grow in intensity, and we have an increasing background here, while, for example, the bismuth lines, they stay rather constant. They have some ups and downs, which have different reasons. So we need to understand this, and maybe I should point out that the integral satellite operates in a highly elliptical orbit, typically 3 days orbit, and the orbit goes out to about 1/3 the distance to the moon. The idea was to stay away from the radiation belts as long as you can, because charged particles make all this background, and you don't want that this comes too frequently. When you have a near Earth orbit with like a 1.5 hour orbit or so, then you get a radiation dose every 1/2 hour, and that's more difficult to trace than when you have a 3-day orbit. And being further away helps. So what we do then, we try to understand this spectra in great detail. So you see that we integrate over long times, and then we find all the isotopes that are responsible for each of those little blips and peaks. We have to describe those in intensity and in shape, because our detector resolution also is a function of time, and we need to characterize this background in great precision. So we characterize it here in energy. We find each of the even small intensity peaks, and we fit it with a parameter that traces the intensity as it goes over those 13 years. We also characterize how the background behaves inside the instrument, because I showed you the shadowgrams from the mass that we need to detect, but those shadowgrams are superimposed on any variations from one detector to the other that the background may have. So we must understand how the background actually creates some shadowgrams that are differences between one detector and the other. Here you see our inner detectors, which are the ones with the small numbers. They are sort of self-shielded from a background that comes from the outside. So the outer detectors see more than the inner ones from bismuth, which comes from our anti-coincidence. While germanium lines are more intense for the interior detectors because they are surrounded by germanium on all sides. And the 511 is yet another case. So for each of the 400 background lines, we need to understand how the shadowgram of background events would actually look like, because detecting any source from the sky implies solving this equation here. Our data in each energy bin and in each detector are driven by the shadowgrams of the intensity from the sky with some intensity factor, and that is added on the background as given by these detector patterns, and they have to be also fitted with some fudge factors, so that in the end these coefficients here, they make the spectra that I will show. This is the intensity that we assign to our source in the sky, extracted from those shadowgrams. So typically when we make a spectrum in, like shown here for aluminum-26, then we have to analyze something like a few 100,000 such spectra, because the data are collected over years. And from solving this equation with the appropriate statistical software, you can then construct the maximum likelihood solution, which is the spectrum. It's made a little bit more complicated because the shadowgrams are actually collected over large regions of the sky. So this is an all-sky map which shows the exposure where integral has been pointing at different times during those 15 years. And you see that the different pointings, they form patterns on the sky that are not homogeneous, because we want to trace, for example, hard X-ray sources that are in the inner galaxy, and those are more often a target than at other times. So we have to trace all these things, all the different pointings and the shadowgrams as they change. We also have to account for the fact that the response is not always a nice Gaussian as you would like it to have, but the cosmic rays actually destroy our germanium detectors. And so with time, the response gets a tail towards low energies, because cosmic rays destroy the charge collection capabilities of a germanium detector. And so every 6 months, we actually turn off our cooling and we turn on the heaters and we cook our detectors for 2 weeks. And that cures this destruction again. This is called annealing. And this leads to a temporal variation of the instrumental resolution that is shown here. And annealing basically restores it again. Then we have the degradation over half a year from cosmic rays, and we anneal again. And so we have a time variable spectral response, which makes the background model again a little more complicated.
Is the annealing equally effective if you go to the lifetime of the satellite?
Yes. Almost. If you look in detail, you will see that the base point is not always the same. It goes up and down, and there's a slight upward trend, a very slight upward trend. But it's not actually affecting our results. But this is a situation that is typical for a source. So this is our background level. And a typical source is a few orders of magnitude below that. So that tells you our background has to be precise to the 10 to the minus 4 or so. And we can do that as illustrated here. So this is a small part of the background spectrum scaled down by a factor of 5 here, just to compare with the sky result that we have. And you see these two instrumental background lines are basically fully suppressed. You see a little bit more fluctuation from Bosonian noise, but we can clearly tell that there is no emission from the sky at these energies, and the high background doesn't confuse us. And here is the aluminum line detected from the sky. You see, when you look carefully, that it's slightly offset from this instrumental line blend that we have superimposed on it. So you see this skyline is only less than % of the total signal in here, but it can be clearly discriminated. So even though I probably scared you by telling you all these difficulties with the background, we can do it. And this is the demonstration that we can do it. So the aluminum case is very clear, and we have several supernova lines that I will talk about. So much about the instrument. Now, this is again the electromagnetic spectrum, and the lines that I want to talk about, they are listed here. There are a few interesting lines. Lines are important for astronomy when they have an intrinsically very different message. So some lines talk about positron annihilation. This is about isotope production and their fate in the universe. Then there are, for example, the recombination lines from highly ionized atoms. They tell us about highly ionized or very hot interstellar medium. This is about recombination of normal material. Then this is about atomic matter distribution, and this is about molecules. So I listed the diagnostic lines, and the nuclear lines are part of that. So my main message is nuclear astronomy will become important, even though the limitations of the experimental techniques are always there. But I think it's worthwhile doing it. And I think we also have been successful. There's a whole large list of results that I could be talking about. I don't have time for that, so I already spent almost half of my time, so I have to speed up a little bit. So I'll use two examples: stellar explosion diagnostics and ejector flows. And let me start with stellar explosions. You probably are most familiar with the explosions of a supernova, and the supernovae that have led to a Nobel Prize a few years ago are the type 1a supernovae. They are used as standardizable cosmological candles. So you can basically measure the brightness of a supernova at different redshifts or at different ages, and that way you trace out how the geometry of our universe evolved. This is what type 1a supernovae are used for, and they have this nice property that after the explosion, after 20 days or so, they reach a brightness maximum, and that falls up very smoothly over a few months. So this kind of light curve is standardizable, and it has a calibratable brightness level that arises from the decay of nickel-56. This is why I showed the decay scheme here, and this is the driver. The decay of nickel-56 provides the energy for this optical display. Now these are MeV photons and positrons that provide the energy, and this is radiation that comes out in milli-electron volts. So you have a polar matter in between. You have some energy conversion between the nuclear energy and the photon energy that comes out. And of course, a physicist wants to understand what we are doing, so we want to understand how is the conversion of nuclear energy that comes out in radioactivity and the radiation that you see in the optical. At the moment, this is based on empirical laws, And the fact that you get a maximum after 20 days means that this radiation is captured. The nuclear energy is captured by the envelope, but the envelope is exploding. So the capture properties get weaker and weaker as the supernova expands. So there's a maximum when you still capture a lot of energy, and then more and more energy leaks out. And what's leaking out is what I want to measure, because it's the gamma rays that are the drivers of this radioactive energy. So the gamma ray light curve has a peak typically about 90 days after the explosion, so much later than the optical peak. And it is the leakage of what you see in the optical. So for us, it was a great achievement that in 2014, we had a type 1a supernova sufficiently nearby so that we could make a successful measurement. And this plot may look complicated. It shows the detail of the two lines that are the brightest ones from this nickel decay chain. This is the cobalt decay to iron. Maybe I can remind you of this. These are the two lines that are the brightest, and they come from the later decay to cobalt. That is at later time when nickel already had decayed, and you then will see a leaking of those cobalt gamma rays. And we have measured them. This is superposition of both lines shifted to the same energy value so that you can see that the line shapes are consistent. And this is even including analysis of two different groups with their two different background methods, because I showed you that background is a driver of the results here. So you see that the lines, they show up broadened, they show up a little shifted, and they are really broadened by a few thousand kilometers, which you expect because you are looking at exploding material. So you would see the Doppler shift of the explosion. This black line here shows the resolution of our spectrometer. So you see the lines really are broadened. They are much broader than our resolution. Now what we have been doing in our group with our very detailed background model, we have looked at the same data at different spectral binning, because that's just the thing that we can choose in our analysis. And then when you look at one of those lines and you see with different binning, you see different things. So our eyes may be misled, and the broad Doppler lines, they are usually modeled as nice Gaussians, broadened, and you measure the width and then you get the velocity. But let's try and use the capabilities of our high resolution spectrometer. And when we do that, then this is another look at the same data. Remember, this is the first time we had an opportunity, so now I'm trying to exploit the data as deep as I can, because it's the first time we get this gamma ray information from a type 1a. So what we have done is we have split that in 4 different time epochs. And here I show you the broad binning. This is 10 keV energy bins. And here is the exactly same data as this one, just in the fine binning that we typically use of like 1 keV or half a keV. And now you can compare by eye what you see here. And I think you would agree with me that it is not a smooth Gaussian line that appears from the background just like a mountain coming up. It's something different. And we know that at typical signal-free phases, we have basically fluctuations within the size of the error bars. That's okay, but we never see something like this, even when we do normal analysis. So this is kind of unusual, even though it's only like maybe 2.5, 3 sigma-ish, but there is structure in the spectra that is beyond what we typically see. It's not typical statistics. There is something to it. And I don't know how to quantify that something because of those error bars. So my message is, we see a structured and an evolving spectrum that is not a simple Doppler broadened line that becomes brighter and then fainter. It is something different, and it looks like that we have a 3-dimensional structure of the supernova that has some regions where you can peek deeper inside the supernova and some other regions where you are more seeing an outer surface only. And that's the message that I think we got from gamma rays, which is interesting. We can look at the brightness evolution also in the so-called light curve. So this is just the intensity in those 4 different epochs. Those are the red data points. And then, of course, you want to improve your time resolution, so you cut it into smaller slices. And you get the blue data points here. But those blue data points, they have larger error bars, and so it's more fluctuation. So again, exploring to the limit, you try what you can do. I don't think we can learn much more from that, except that those models here that have a very slow rise, they are basically ruled out. But all the other models, they basically seem to match expectations. These are all one-dimensional models because people have believed so far that the 3-dimensional structure of a type 1a is unimportant because it was not really driving the light curves. And so one said, well, let's ignore that. It's a spherical explosion. The nickel...
Different spectra at different times, if those peaks are real, and people thought of possible reasons.
Yes, well, as I just described, you could think that you have some clumpy explosion where you have some occulting material lying over some nickel blobs. And so if you have a structure like this, then we have been able to model what we see with 3 major blobs of ejecta that sit at different optical depths. So it's just not a smooth one-dimensional spherical explosion. And the other important thing is this is the measurement of the nickel mass, because in the optical you see only optical light that you can interpret in terms of a nickel mass, but you need a conversion factor, and that's usually a so-called Arnett's law is being used. A certain brightness is converted to a certain nickel mass, but you need to calibrate that. Here we have a calibration because we see the nickel decay directly. We can count the photons, so that converts to a well-defined nickel mass of half a solar mass in this case. This is a very important additional calibration. Well, here is the decomposition into those 3 different blobs that have their different light curves. And here is what we would see if we would have a next generation detector. We have integral flying, but if we had current technology and we would have a satellite now, if you give me 2 billion and we build together a satellite, then let's do it. And the same supernova would have those error bars. Wouldn't that be nice? That's not the case. So we have to live with what we have. And here I show you another characteristic of the supernova explosion, namely when you look out to late times, then you want to know, is my bolometer actually well behaved? So when it becomes really transparent and I have late input from the late tail of the cobalt decay, is that still a consistent picture? And you see the black line here shows the energy input, and the blue data points here, they show what has been measured for a supernova. So depending on the deposition engine, if it's the gamma rays or the positrons, at late times, the gamma rays practically all leak out, as you see here, and the positrons take over beyond about 400 days. Because 400 days after the explosion, a supernova is so diluted that you don't stop any gamma rays, they all come out. But charged particles, they are trapped by magnetic fields. Now, we don't know what the magnetic field in an exploding supernova is. So that part back here is very uncertain, but it's important to find out how radiation transport actually works. And so we were looking at the positrons. You see 20% of the decays lead to positron emission. And positrons can actually also be seen in a gamma ray line that comes from positron annihilation. And that is the marginal signal that we have seen in the 511 keV line that results from annihilation of positrons with electrons. Now that's a very weak feature, but if we take that at face value, then our conclusion is that all the positrons that we are seeing in the initial phase, in the first 150 days or so of the supernova, they are annihilating locally, so they don't escape. And that's a nice measurement to have. It's follows expectation, but it's important to know that.
The fact that 520 is just the result of getting probably.
Yeah. Well, yeah, that's we see this kinematic shift. That is the same kinematic shift that we see also in the other lines. You saw that the other lines also were not at 1238 and 847. Okay, they were at slightly higher energy. So the shift is the same, luckily. We had, at the occasion of the supernova, we had seen something spectacular that was actually responsible for make me some enemies, because I was reporting that very early and nobody believed that. And so I was kind of in a difficult position, having found something exciting, but we wanted to wait until we have the nice result from 40 years of waiting to publish the cobalt lines. But we also saw the nickel lines. That was very early, and actually several of my colleagues also saw that hint. And it took us about 2 years to digest the different analysis methods and to really agree on that. And now all my colleagues also agree there is nickel in the early part of our data, and we shouldn't be seeing that because the nickel decays at 9 days. And this was measurement that started only 20 days after the explosion. So the nickel should have gone. But we saw the nickel lines with hints that are like 3 sigma-ish, so it's not too bright, but it's clear that this is a significant excess over the background, and I showed you that we know what we are doing here. So this converts to about 10% of the nickel mass sitting on the outside, and that was quite spectacular, and it also is against the standard picture of a type 1a explosion. So maybe we can learn something about 1a explosions from doing this radiation transport. So I think we learned that maybe models like this can place some nickel on the outside when you have helium sitting on the outside, and you actually explode the helium first from the outside. That sends a shock wave into the white dwarf that leads to the final ignition. That is one way of having nickel outside, because the helium burning creates a little bit of nickel. So that's one way of doing that. People are discussing different models for type 1a explosions, and the binary systems where a helium white dwarf or a helium star actually leads to accretion on the white dwarf is quite a plausible scenario. The double degenerates, for example, they would be just like that, where a helium white dwarf transfers some mass onto the companion that leads to a helium flash that sends the shockwave. So it's interesting that we are part of reviving this discussion about the progenitors. If you look at the recent review papers about type 1a explosions, the list of progenitors is typically long. There are maybe 20-something different scenarios how you can make a type 1a supernova explode. And it's a very active field. I'm now switching. In 1994, with the Compton Gammaray Observatory, we measured this spectrum from this region of the sky. This is a location map of the signal that we got, and that was Anatoly Yudin's achievement. He reported this line. You see, it's now a scintillation detector, so it's a very, very broad line, but it sits at the right energy of titanium decay, and that was a great surprise, but it was the start of much work on titanium-44 that is based on this decay chain here. So titanium decays within 85 years through electron capture to scandium-44, which then quickly decays to calcium. And this was the line that Compton saw, the line at 1 MeV. Now, Compton was not the only one. Then we looked in the OSSI instrument, and that was a marginal or insignificant result. The same with RXTE and Beppo-Sachs. And with integral, we made a measurement that was then much better. And this is the new star measurement that was even more precise. Now, all of those later measurements, they were done on these hard X-rays, while the Compton measurement was on this line. It should be the same decay chain, so they should all be consistent, but I will show you in a little moment that this is also an interesting consistency check. Now, the key achievement of the NuSTAR mission, I think, is this image. That is a textbook image, and that is showing you a titanium ejector image resolved in a supernova remnant. The JINA CEE supernova exploded 350 years ago, so it's many lifetimes of titanium, but we could see the titanium with Compton, with integral, and with NuSTAR, and NuSTAR was able to image it because at that distance, this is a source that basically fills their field of view. When the source is closer, then they have to do, they basically have to do different mappings, and when the source is further away, it looks like a point source to them. So this is at the right distance. This is basically the one and only source where they can do something like this. It provided a great textbook result because it shows these bluish emission regions where the titanium sits. And you see, this is about a handful of clumps of titanium that comes out of the supernova explosion. I think this is a fantastic demonstration to the eye that a supernova explosion, like in the case of JINA CEE, a core collapse, is exploding in fragments. So ejecta come out in fragments. And the titanium comes out from the inner burning of this core collapse. And you see this is superimposed on another image that has been used for decades on JINA CEE supernovae. It's based on X-rays. So this is X-ray recombination lines, and the reddish ones, they are the recombination lines from iron. So at that time, it was, the interpretation was that the iron is sitting on the outside, the greenish stuff is silicon. And so it was always believed that there is a puzzle about the inversion because a massive star should have the iron sitting in the inside, the silicon and the lighter material sitting further outside, but the image in X-rays shows the opposite. And now with the titanium, the puzzle was rekindled because you saw that the titanium and the iron, they don't sit at the same location. But they should be according to expectation because both those heavy materials, they come from the inner burning at nuclear statistical equilibrium with alpha-rich freeze-out. So that should all happen in the core of the supernova. So where you find iron, you should find titanium and vice versa. And the silicon should be sitting outside. Now what the NuSTAR image shows, the radioactivity here shows these clumps, and the iron is a recombination line that needs the iron to be in a state where it can emit recombination, though it needs to have an electron that can recombine. So when you have fully ionized iron, you don't get the X-ray line. And that's the explanation for this discrepancy. When the ejecta are fully ionized, there is no X-ray emission. And so we are learning about the biases in different observations, and people are now interpreting this and trying to build models. And this is a great achievement, and these are the details of this result, and NuSTAR is really a fantastic contributor to our nuclear astrophysics. NuSTAR also has a large instrumental background, just like other instruments have, because it's the same physics that applies, cosmic rays, excite, and so they had to use their background model that you see here, and then this shows the difference between the background and the total signal, and they are actually doing some kind of background subtraction, and then they show you this result as a result of the background subtraction. I don't want to go into details. I just want to tell you, when you are diving into nuclear astronomy, you have to deal with background one way or the other. There's no way out. But you can do very nice things. And NuSTAR has, for example, due to their imaging capability, they could analyze spectra in different parts of the image. And that makes a detailed map of how the ejecta are actually flowing one way or the other. That's a detailed result that I'm proud that we could basically confirm that with integral, because with integral we can actually also measure those same lines and they are really very difficult to detect because of the instrumental background that I superimpose here again. It's similar to the new star problem. We don't do subtractions, so it doesn't look so significant, but the high energy line here is also significant and can be compared to. What we can also do, we can compare the high and low energy lines. So these two data points are from the calcium line that is at 1.1 MeV, and these data points are the low energy lines from the different instruments. And so we see that there is a discrepancy that we still have to understand, because it's the same decay chain that should actually be the same, and maybe there is some particle acceleration of the titanium once it has decayed to calcium-44. Then when you have a nuclear collision, you can make excited calcium also with cosmic ray interactions, and that may make the MEV line a little more intense. All in all, this is the summary result on CAS-A comparing different regions. So this is the detailed result from New Star from one region, where you clearly see that there is some redshifted parts, so that there are some ejecta moving away from us. And we are seeing the same thing when we look at the high energy line. It should appear at this position, but we see a line that is slightly redshifted. So in general, from CAS-A, we learn it's not a spherical explosion. We have three-dimensional structure, and we have to try and understand these morphologies of supernova explosions. Now I realize I have to skip over some material, so let me just go quickly and go to the diffuse emission, sorry. I'd like to continue with aluminum-26 for the last 5 minutes or so. This is the map of aluminum-26 as we have obtained it from the Compton observatory at the time. So this was imaging with a Compton telescope in the aluminum-26 line, and that shows us a map of the radioactivity in our galaxy, or in other words, of nucleosynthesis in the current galaxy, because this is a lifetime of 1 million years. Many sources contribute during this 1 million years. So every contribution of aluminum-26 from a nova explosion, a supernova, a Wolf-Rayet star will add up to the picture that we see integrated over 1 million years. Now our galaxy is something like 12 billion years old. So the last 1 million years is what we see here. So it's current nucleosynthesis in the current galaxy. Now that image was important because it was not smooth. It showed some star-forming regions like here and there being sources. And so young and massive stars are most likely and most plausibly the dominant sources. And the nova contribution is probably small because the supernova rate is typically 1 every 100 years or so, while the nova rate is 30 or 40 per year. And so if it were novae, it would be a smooth distribution by many, many millions of events that you would superimpose, while here this is rather structured. So with this image, now we can look from these gamma rays how much aluminum we have in the galaxy. We can basically turn the amount of photons that we count into a mass of aluminum-26 isotopes, and the equivalent of 2 suns only in this isotope we have spread over our galaxy. And that's an interesting number because you can turn that into a supernova rate by using some additional assumptions. So when you use the geometry of the galaxy, then you can turn the flux into this number here. So that's our latest number, and I will say a few words about that in a minute. But 2 solar masses in our galaxy with an uncertainty of something like 0.3 solar masses, and you can use then the typical yield per star in for massive stars, which is shown here. to turn that into a core collapse supernova rate, and that would be 1.3 per century. So this is the measurement of a massive star supernova rate with nuclear lines that are accessible through the entire galaxy. And all the other measurements that you see here in this chart, they are based on a different method. They are, for example, counting O stars near the sun, or using supernova rate measurements in galaxies that are similar to our galaxy. So it's important to compare the same measurement from different systematics, and that's what we have been doing here. And so we are happy to have this number from the nuclear lines sampled over the entire galaxy rather than just from the solar vicinity. Now, this number, we had a higher number before, and that depends on where you place your sources. When you look at the image, maybe I should go back to the image briefly. Here are some source regions that are really very nearby. And in the initial estimate, we have basically ignored those. But when you have a source that is nearby and you use a geometry model because the distance is intrinsically unknown, and you place those source regions to 8 kiloparsec, typically to the inner galaxy, then you get a different value. So accounting for the very nearby emission that comes from this cosine region changed that number from the 2.8 that we had before to the 2 solar masses. So that's not the last word. I want to just illustrate that this depends on the assumptions that you make where your sources are in terms of distance. One final aspect, we have a germanium detector which has a high spectral resolution, and so the aluminum line is shown here in different plots, and you see that the line seems to be located at a different energy. This is the Doppler shift from large-scale galactic rotation, because we sit here in, this is the galaxy in a top view, in the location of the sun, and the large-scale rotation leads to a red shift when you look in this direction, and a blue shift when you look in this direction. And we were actually surprised that we were so sensitive we could actually trace that. So our precision in velocity is a few 10 kilometers, where we can trace this motion in the galaxy. This motion was known before, but we didn't know that we could trace it even in gamma rays, and that's a very high velocity resolution. Of course, when you measure something like this, you want to compare if you measure the right values. So we were measuring shifts of about 200 kilometers per second, depending on where we are looking, plus or minus 200. So the green data points are the velocities from the previous plot. And when we compared our numbers to other objects that are rotating in the galaxy, our numbers were way too high. How can that be? These were the numbers that, for example, the color plot here is what you measure in carbon monoxide. Those are molecular clouds, and they are quite turbulent in the inner galaxy, but in the outer galaxy, they don't go beyond like 100 kilometers per second or so. So we measured very high velocities, and we were scratching our heads for a while until we came with this explanation here. So this is the plot that I showed you before. This is the location of the sun, and we are looking at the spiral arms of the galaxy in a geometry that looks like this. And now when you imagine a spiral arm is a higher density of material. Now assume this would be a molecular cloud that comes into the spiral arm from the back end. That's how the geometry works in our galaxy. Then the higher density compresses this molecular cloud, and it will form stars. Now the stars being formed here, they have to evolve, and it takes a few million years for them to evolve. And then the first stage of evolution of those stars is that they blow strong winds. They are Wolf-Rayet stars. And when they blow strong winds, they basically blow a cavity around them. Now, by the time they do that, they have been moving to the forward direction of the spiral arm, so they sit at a density gradient. This is the empty interarm region. This is a spiral arm density. So the cavity will be asymmetric. They blow a bubble, and this bubble will be more extended in the low density regime compared to the high density regime. And now when you have such a cavity and you make a supernova explosion, or you eject radioactive material, then the radioactive material will have a longer time to travel in the forward direction than in the backward direction. So you will see more aluminum decaying while it is still traveling in the forward direction at high velocities, while in the backward direction it will be decelerated by the boundary of this cavity. And that leads to a bias in the velocity in one direction, and that is the same in both directions of the motion. So the extra 200 kilometers are explained with this model in this green dotted line. So in essence, we have learned here that ejecta are preferentially spread out in superbubbles, and this is the way how nucleosynthesis ejecta go into the interstellar medium. And so the puzzle is, how do you find such ejecta in metal-poor stars? You first have to solve this transport through a superbubble. This is hot, this is 1,000,000 degrees hot. You have to cool it, and these superbubbles are regions that are not forming stars because they are so hot. So there is a conversion problem of ejecta from a supernova into new next generation stars that is illuminated by this. And it's a picture that has emerged only recently in the last 10 years or so from theory and also from our observations. And with this, I am at the end of my messages. I just want to go to my final slide. I had a few other things that I would have been able to talk about, but let me just skip those. So these are sky maps in different spectral ranges, and you saw the aluminum map. This is the map that we have in positron annihilation, and those two maps come from the field of nuclear astronomy. And these are lower energy maps in the radio and in the optical. This is at high energy gamma rays. And so my bottom line is, nuclear astronomy really is worthwhile. It's a complementing picture that tells us new physics. And the physics messages are summarized in this slide. And with this, I would like to thank you for your attention and for your patience to listen to me for more than 1 hour. Thank you very much.
Thanks, Roland, for a very nice talk. Other questions for Roland? Yeah. Is it possible to reproduce the shifts you're seeing in the gamma ray spectrum by actually simulating the source of the
in the case of the aluminum, you mean? Yes, that is actually what we did with this green dotted line that I showed. This is a result of a simulation where we put the sources along the spiral arms, and we impose the velocity spread that you expect from such cavities. I showed you that when you have other galaxies and you can see them face on, you see also typical, in H1, you see some structures that are like voids in the galaxy. And so I think this picture is supported, and we used that picture for our simulations. So,
Has it titanium received any other supernova?
Titanium has been measured with NuSTAR on 87A.
Yeah.
So that has been measured. We tried to measure it with integral, and there is sort of conflicting results. There is a result from based on EBIS largely, where there were images made in 3 different spectral bands around the hard X-ray lines, and that showed a slight excess. Then we, in our group, we tried to analyze with a spectrometer. We cannot see a signal from 87A. So I think that number, the number that they published, our Russian colleagues published from the EBIS result, was a little bit too high. So this is typical when you have this high background situation and you ride on some noise enhancement, then typically our fluxes get too high. So I think the NuSTAR measurement is a very nice measurement from 87A, and integral has some indication, but not really a number. But we are actually, I should comment, we are expecting a handful of such supernovae in our own galaxy from core collapse rate. I showed you that the core collapse rate is determined with aluminum-26. When you use that rate, then you should see 5 titanium sources in our galaxy. The fact that we only see one, namely Cas-A, which is already 350 years old, and we see none in the inner galaxy, tells us that titanium production is a rare exception in core collapses. Sorry, you had a question.
Yeah, you saw a huge Doppler body from your core, but then when you look at positrons, then we have the chart. So what is positrons stop
Yes, that's an important question, because the annihilation only happens below an energy, you have 6 electron volt or so. So you need to slow down the relativistic positrons to make them annihilate. And this is ionization and Compton collisions. So it's basically the typical slowing down that happens in the gaseous medium. And so the fact that we see the annihilation line means that the supernova in the initial 100 days is dense enough so that you have a sufficient number of collisions to slow down the positrons. And this must be interactions or collisions, Coulomb collisions with charged nuclei or with electrons. So that's the result that we see. You must have some slowing down interactions, as you expect in any volume of gas, but it must be dense enough so that you get the annihilation working. This may not be the case, for example, when you have a neutron star merger, because the neutron star merger gets diluted very much more quickly, and it's less material, less overlying material, so that there the charged particles may have a higher chance to escape. And there are other positron sources that we have seen, microquasar flare that we have seen. There we believe that most of the positrons actually do not have a chance to interact with other electrons, unlike in the supernova, and most of it escapes. That is an interesting, our hypothesis to explain the annihilation that we see in the galaxy. The image that I showed you is probably due to the fact that most positrons typically escape from sources. Not so in the type 1a.
Daniel?
Your coded mass also showed an image of how you have Gammaray coming in and it's the first array and then it goes down and it's the second array.
That's in the Compton telescope, yes.
Right.
That's not the coded mass, Compton telescope. Mm-hmm.
How are you differentiating between whether Gammaray comes from the top versus the bottom? What's the difference?
You need high time resolution electronics, and that was the limitation. So at the time of Compton, we had the typical separation is 3 nanoseconds, and so you need to have something like a sub-nanosecond electronics, which is hard to do when you have spacecraft electronics where you don't have high power. But in the last 20 or 30 years now, people can do like half a nanosecond or so. It's not a problem for electronics typically.
Do you record the events that come in backwards?
Yes, yes, yes. That's actually the backward events are much more abundant. You have a much higher rate because in the case of the Compton Observatory, we had a low Earth orbit, so we were sitting at 500 kilometers. Basically, the Earth was always underneath, very close. And so most of the terrestrial gamma rays, they come from below. And so the backward or the wrong events were about a factor of 50 higher than the forward ones. And so when you used a Gaussian to fit your timing of the forward events, the tail of the Gaussian was brighter than what you would see from the cosmos. You would have, you had to use actually the right line shape for the timing distribution of events. So Gaussians is not always a good thing. But it's this is the challenge to Compton telescopes, to build 2 detector planes where the detector electronics is very sensitive to lowest energies. You want a low energy threshold, so you want to work with something like 10, 20 keV ideally. and then do that at the time resolution of picoseconds. Not easy.
Okay, I think we better wrap up. I think Roland can stick around for another 10 or 15 minutes in this room if anybody wants to have further discussions or maybe hear about Iron 60 or something.
Sure.
But,
yeah.
Let's thank Roland again for nice talk.
Thank you.